that just gets me understanding what's probably coming. And then you read it, and sure enough, that's exactly what's happening. Right? Angie's riding an electric scooter. She accelerates at a constant rate away from her starting point for 80 seconds. Right? And now we can read this and sort of follow the graph as well. Then decelerates and comes back to rest after 40 seconds. So she's hitting the accelerator, going faster and faster and faster. Then she hits the brake, goes slower and slower and slower, and stops after 120 seconds. Right? She waits for another 20 seconds just standing there, right, before turning around and accelerating at a constant rate towards her starting point. Sure enough, she's going the other way, so this is negative. Right? So the graph is not going to go that way now. It's going to go down here. Right? Excuse me. She's accelerating at a constant rate, so it should be a straight line going down. If we have to draw it, it looks like we do. Towards her starting point. She arrives at her starting point 80 seconds later, so that's 120. So somewhere along 200, this is going to stop. Right. Figure 1 shows the velocity versus time graph for her journey, or for part of the journey. All right, let's have a look. Show that Angie has traveled 480 meters away from her starting point when she comes to rest. Okay, that's the point when she came to rest. Now I want to show you something here, just in case you're unaware of it. This is how to manipulate graphs, okay, in physics. The graphs are always either displacement versus time, velocity versus time, or acceleration versus time. This one's a velocity one. And to start with one of these graphs and to get one of the other figures, one of the other quantities, this is what you do. Right? Each of these is the rate of change of the one before it. Right? Acceleration is the rate of change of velocity. Velocity is the rate of change of displacement. And the rate of change is the gradient, right? Delta y over delta x, rise over run. You've probably known that for about 3 years from maths. Okay, so if you are looking at a displacement versus time graph and you want to find the velocity of something from that graph, you get the gradient of that graph. Right? If you're looking at a velocity graph and you want to find the acceleration, you get the gradient of that graph. Right? If you're going the other way, it's the area under the graph between the two times that you're looking at it, right? If you're looking at a velocity versus time graph, which is what we're doing now, and you're asked to find out how far something went, which is exactly what we've been asked, we've got to get the area under the graph. So that's what we're going to do. If you're not familiar with this, this is a great thing to put on your cheat sheet for the exam, right? Pause this, copy it, whatever. Right? Very useful information. This crops up a lot, and it's cropped up right now, so let's get to this question. Okay, I've got the working over here. It's the area under the graph between t equals 0 and t equals 120. Another shortcut for you, by the way. This is a triangle. Every triangle is half of a rectangle, which is why the formula for the area of a triangle is a half base times height. Base times height is just length times width of a rectangle, right? That triangle there, I'm going to redraw it here. That grey triangle is exactly half of this green rectangle. Right? Every triangle can be drawn within a rectangle, and that's the base, and that's the perpendicular height, and that's also the length and the width of the rectangle. Right? But that area there is half of the entire green rectangle, and that's why the formula is what it is. So you can calculate the area of this triangle the long way. You can be counting squares and split it into two triangles and do this formula or whatever. Or you can just go length times width and then divide that by 2. Right? That's the easiest way to do it. Always find the fast way. Right? Life is too short for the slow way. Okay, so this is what I did. 120 times 8, right? And then halved it, comes to 480 meters, and that's exactly what they told us it should come to. Right? So that's the working you have to put in there. Okay, that is part A. Part B, what is Angie's average speed during the 120 seconds? Average velocity, displacement over time. Right? First displacement in the 120 seconds is 480. Time is obviously 120 seconds. Answer's 4. Easy. That's why it's only worth 1 mark. There's almost nothing to do. That's very easy. Okay, I made a mistake down here. Ignore that. Let's pretend I'm perfect and I didn't make a mistake. Let's slide this across to here. Let's just glaze over that and pretend it didn't happen. It's not like we're recording or anything. All right, C. Determine the magnitude of Angie's acceleration as she travels back towards her starting point. Show you're working. Now, when in doubt, in a calculation question, excuse me, in physics, do this first. Just write down what do you know. All right, so this is about her trip back. It says, as she travels back towards her starting point, show you're working. Let's have a look at the graph again. So we're talking about this trip. It starts there at the 140-second mark. Remember, she stopped for 20 seconds. So it starts there, and then somewhere around here, we don't know what the gradient of it, but it's going to end about there. So we know the time. Right? And I've just realized I've drawn these gray dots at the wrong number because she stops 80 seconds later, and I've gone 60 seconds later, so let's pretend that didn't happen as well. Doing well. Okay. So we know how long it took, right? It even said, I think, up here, she arrived at the starting point 80 seconds later. So the time that this journey is going to take is 80 seconds. Her starting velocity is 0. She began at a velocity of nothing, right? She's going 480 meters because she has gone away 480 meters and she arrived back at her starting point. So she's come back 480 meters. So she started at 0, she's traveled for 80 seconds. In that time, she's managed 480 meters. We know she was getting faster and faster and faster all the time because it said she was accelerating at a constant rate. What's that constant rate? Right? And once you've got this right, this is pretty much all the physics, right? From here, a grade 8 kid could do this. A decent maths student from grade 8 or 9 can do this from here, right? You have to pick one of the formulas, you have to pick the right equation of linear motion, and again you should probably have all of those on your cheat sheet. You have to pick one that's got U, S, T and A in it and hasn't got V because we don't have V, we don't have a final velocity, right? And that's the one. S equals ut plus half at squared. Put the numbers in. U is 0, so that bit completely goes, so it's a half times A times t squared. Solve it for A. That's the answer. All right, but all of the brain power, all of the smartness is getting that list, right? Once you do that, grade 8 maths. Okay, D. At what speed was she traveling as she returns to her starting point? Now this is for the same trip, so you can use the same figures. Right? They're talking about her journey back because they haven't said, they haven't said that we're suddenly considering another time. So this is a continuation of C and D are for the same journey. So same figures, now we're finding V, her velocity at the end. Pick a different formula. V equals U plus AT, U is 0, A now we know, T is 80, bang, 12 meters per second. So she's going to hit her starting point traveling at 12 meters per second. Pretty fast. Okay, E. Complete the graph. Okay, so having known all of this, complete the graph. So here's how to do it. So we know she's starting her return journey there, right? She stopped after 120 seconds and she stayed motionless for 20 seconds. She waits 20 seconds before turning around, right? So she begins there. She ended up doing 12 meters per second when she got back. So this is velocity. So that minus 12, keep in mind we're going back the other way, right? At the 220 mark, after 80 seconds of travel, she had sped up to 12 meters per second. So she's got to get there. And she was accelerating at a constant rate, so it's going to be a straight line. So the way to continue it, or to finish this graph, is to just do that. Answering questions C and D gave you all of the little bits that you had to get, and then you could piece the rest of it together. So you need to draw a straight line from the point 140, 0 to 220, negative 12. Okay. Part F. Describe how the speed versus time graph of Angie's journey would differ from the graph in figure 1. Justify your response. Once again, it's easier for me to show you. I'm just going to show you the graph again. The pink line is velocity. Speed doesn't have direction, right? Direction is ignored. It's just how fast are you going, right? And so there wouldn't be positives and negatives. So this would be the same. The first bit would be the same, but this wouldn't be, we wouldn't have bothered to do negative So instead of going down there, we'd have gone up to here. Right? She finished off going 12, so that would be the speed line. Now, by the way, it's absolutely fine to answer question F over here by saying, see line that I've drawn on graph, labeled F. And then go over here and do that and just label it F. Right? That's really clear communication. Everyone's going to give you full marks for that. Right? Or you can just describe what would happen. Right? The return journey is positive with a positive gradient rising to that instead of descending. Right? And the reason for this, right, is that speed direction is ignored. So you don't need positives and negatives. Okay? Because they did say justify your response. So over here you'd have to justify it. All right. That, my friends, is the end of question 1. Question 2. There it is. Okay. Here's the question. Reading it out to you. You've got it in front of you. Zoe is standing on the ground. Here's Zoe. I've got the drawing here. Zoe is standing on the ground beneath a bridge. And Jay is standing directly above her on the bridge. There's somebody there. I haven't drawn Jay. I haven't drawn anybody. Zoe throws a ball vertically upwards at Jay, or to Jay, at a speed of 16 meters per second. Determine the maximum height that the ball reaches above the ground. Okay, so this is the trip, the pink trip there. That's what we're doing. And again, all of the brains is in getting the list of quantities and then just picking the right formula. Once you've got this purple bit done, it's grade 8 maths. Right? The year 11 physics is figuring this out. So let's sort this out. So, just going to pick a color. That's from the start, that's the end. Now, at the point that it gets to its highest level, its vertical velocity is 0. It might be going sideways a little bit, but it certainly isn't going up and isn't going down at that point, at that little moment. Right? So that's why I put V as 0. She throws it vertically at 16 meters per second. They told us that. So it starts off at doing 16, and of course it starts slowing down because gravity's pulling it back. It goes 16, 15, 14, 13, 12, 11. Eventually it's going to stop rising. And you know that it's going to slow down by 9.8 meters per second squared. Right? That's the acceleration due to gravity, and you have to put the negative in. Right? Because there are two directions here. It's the ball is traveling up and accelerating down. It's being pulled back. That's why it's slowing down. So the positives and the negatives matter here. Right? So that's the list, and we're going to find S. Right? Determine how far it went. That's displacement. That's S. So VAUS, we've got to find a formula that doesn't have T in it because we haven't got it. That's the one. Right? Solve that formula, plug all the numbers in, solve for S. Turns out to be 13 meters. So the highest point in that trajectory is 13 meters. Part B. Jay catches the ball when it's moving downwards at a speed of 4.6. So she throws it up and it goes higher than the bridge. And then it comes down and lands on Jay and Jay catches it. Right? So this is a different trip. Right? So this is a different journey. This isn't the journey to the top of its rise. This is the journey to finally getting onto the bridge. So you have to scrap those figures and get a new list. It's a little bit different. The initial speed is the same. Right, 16. Acceleration is the same, still on Earth, but the final velocity is not 0 here. The final velocity is 4.6 meters per second down, so it has to be negative. Right. And again, find S. Right. And as long as you've got these figures right, this will just do it automatically for you. And sure enough, it's easy enough to do. The S turns out to be 12 meters. So the bridge is 12 meters above Zoe. And she threw it basically about how far? And she threw it 1 meter too far. So it only went 1 meter above the bridge. I massively overestimated the drawing. Right. But that's the important thing. Getting those purple lists correct is pretty much all of the brains in doing these questions. Okay, part C. How long is the ball in the air before Jay catches it? So from the moment that Zoe lets go of it on the way up to the moment Jay catches it on the way down. So it's the same journey as part B. It's from Jay, not to the top of the rise, it's from Zoe to Jay. Right. So it's the same figures as B, and you have to find the time, right? V equals U plus AT, solve for T, 2.1 seconds, easy enough. All right, question 3. Here's the diagram. I've reproduced it here in a very rough manner. Josephine and her bicycle have got a combined mass of 80 kilos. We might use that later on. Let's just stick that there. She's gliding down a hill, Right? That is useful. She's not accelerating, she's not slowing down, she's gliding. Right? She's not pedaling. With an incline of 25 degrees. Okay, no resistive forces on Josephine. Okay, there's no friction, no air resistance. That we're not going to take those into account. We know they're there, but we're pretending they're not for this. On figure 2, draw the forces acting on Josephine using labeled arrows. Okay, this is the answer. There is gravity and there is the normal reaction. Now the normal reaction is called the normal reaction because normal means at right angles. And that reactive force is pushing always at right angles to the surface that you're on. Excuse me. So it's not straight up. It is an action-reaction force, but it is reacting to the component of gravity that's in that direction. That's at right angles to the surface. So they're the two forces on it. And there isn't anything else. They said there's no friction and air resistance, so that's all you have to do. 2 marks. Explain why Josephine does not accelerate at 9.8 meters per second squared. Okay. Anything that's falling accelerates at 9.8 meters per second squared, but you have to be falling. You have to be going straight down, and there has to be nothing trying to stop you from going straight down for you to get that 9.8 meters per second. She's not falling, she's going down a hill. Right? The closer that hill is to vertical, the closer to 9.8 seconds you're going to accelerate. So if you ever find yourself riding a bicycle down a hill like this, it's going to be terrifying because it's almost vertical, and you will accelerate at almost 9.8 meters per second squared. And you're going to die of fright if you don't die of landing at the bottom. Excuse me. The more gentle that hill gets, the more close to horizontal that slope gets, the smaller the fraction of the 9.8 your acceleration is going to be. And you can calculate what fraction of the 9.8 your acceleration is going to be just by using some simple trigonometry. And I've done it down here. Let's have a look at this. So here's how I would phrase the answer. So the acceleration of something that's falling vertically is 9.8 meters per second. On that slope, on this slope here, the acceleration that she does experience is the component of 9.8 meters per second in the direction that she's going. Right? So there is a vertical component to that direction, but you have to figure it out from here. Right? Now to find the components of a force, this is what you do. You make the real force the hypotenuse of a right angle triangle. We've done this before, but not for a while, not since about the start of term 3. So this is hopefully all coming back to you now. Right, but the real force, the thing that's really happening is the hypotenuse of a triangle. And you make one of the other sides of the triangle in the direction of what you're interested in. In this particular case, that direction there. Right. And if that's 25 degrees, then down there, that's 25 degrees, by the way. All right. So that would be exactly how I would answer that question. Right? The acceleration is less than 9.8 because it's the component of 9.8 that's in the direction of the slope. All right. Now part C says determine the magnitude of the force exerted by the brakes. So she applies the brakes. Sorry, just let me get the question back in front of you here. Right. She applies the brakes on a bicycle so that she travels down the hill at a constant speed. So she's not trying to stop, she's just trying to not go any faster, just maintain a constant speed. Once again, that phrase, constant speed, has some meaning. Constant speed means that the forces on her add up to 0. So whatever's pulling her down the hill is going to be perfectly balanced by whatever's trying to stop her from going down the hill, in this case the brakes. Right. Excuse me. Okay, so in other words, the brakes have to match whatever force is pulling her down. And the force that's pulling her down is gravity. Right? If she was falling, it would just be mg. Right? So we know the force of gravity is just F equals mg there, right? But she's not, again, she's not falling, so it's not that strong. It's the component of this in that direction. So we're going to do the same thing. We did the same thing up here. We're not really doing it with the acceleration here. We're doing it with mg. We're doing it with the acceleration times her mass. So this is that times the sine of 25. Right? Simple trigonometry. Ask me in class if you don't know how I got sine of 25. So it's 9.8, it's mg. I forgot to put the m in first, sorry, that's why I tacked it on to the end. It's mg times the sine of 25. So that's 330 newtons. So we've calculated that the effective gravity down the hill is 330 newtons. And therefore the brakes must be applying 330 newtons in the other direction so that she's not accelerating down, she's not speeding up, she's not slowing down, she's just going at a constant speed. The forces have to add to zero. They're cancelling each other out. All right. Now we've seen this one before, earlier in one of the multiple choice questions. Explain why the force exerted by the brakes is not considered to be an action-reaction pair with the force causing Jacqueline to accelerate down the hill. This is that equal and opposite thing. This is Newton's third law. Action-reaction pairs are equal and opposite. So here's how you work it. Right? Remember we had the sphere on the rope or something? It was one of those multiple choice questions. Let me see if I can grab it. Yeah, the cart. Remember this one? Rope pulling on the cart, cart pulling on the rope. Same sort of thing is being tested here. The force causing the acceleration down the hill is the earth pulling on the bike, right? The equal and opposite one there would be the bike pulling on the earth, and that's not happening. Right? The brakes are pulling the wheels. The brakes are forcing the wheels, right? So force pulling it down the hill is the earth forcing the bike down the hill. The braking force is the brakes trying to force the wheels to stop moving as fast, right? They're not acting on opposite things. Those two words don't appear in this. Right? If it was equal and opposite, those two words would be right there, or those two would be right there. Different things. And that's all you have to say. Right, last one. When she's traveling down a hill, the normal force exerted by the ground is less than when Josephine travels on a horizontal surface. Explain why it's less when she's traveling down the hill and use a calculation to support your answer. Okay. This is a bit repetitive now. The normal reaction reacts against the component of gravity at 90 degrees to the surface. It's reacting to this. It's not reacting to that. Okay. And this is that. Okay. So it's a little bit less. And if this is mg sine theta, that other one is mg cos theta. So this is the calculation that they're after. Okay. So in this particular case, the normal reaction is not mg, it's mg cos theta, and 80 times 9.8 times cos of 25 is 710 newtons. I've just realized that that little calculation that I was pointing to was too low for you to see, so there it is. Okay, that is it, I believe, for question 3. Question 4, okay. This is an impulse and momentum question because this is about collisions. Right, it says, a car manufacturer is performing a crash test for their new car model. A 2,000 kilogram van and a 1,200 kilogram car are driven in the same direction, excuse me, and the van collides with the back of the car. During the collision, the van experiences an impulse of 6,000 newtons. After the collision, the van and the car continue to travel in the same direction as a single object at a speed of 27 meters per second. Okay, let's unpack this a little bit. There's a lot to take in there, so I've sort of drawn a summary. So this is what's going on. Before the diagram, before the collision and after the collision. So they're both going in the same direction. Now it's important to call one direction positive and one direction negative, even though these things are going in the same direction here. That'll become obvious later on. So we don't know how fast either of them is going at this stage, but we know that the truck's going faster than the car because it catches up to it and hits it. And we also know that after the collision, the two of them slide along together at 27 meters per second. That's what they've told us. Right? Now, these are the formulas that are involved with collisions. Right? I should probably add one more thing, conservation of momentum. Right? The total momentum of any bunch of things that are going to collide before the collision equals the total momentum after a collision. In every collision between any things, doesn't matter if it's more than two things, by the way, but you'll only get two in these exams. In any collision, the total momentum of everything that's going to hit each other before the collision is the same after the collision. And we use that quite a lot. Now, the other thing that is often used in collisions is impulse. Impulse is the effect of a force, right? When it collides with something. And it's basically the force multiplied by how long the force was acting. That's what the force ends up doing. It's also equal to the change in momentum of something. Right? What the force on something does is change its momentum. So we're going to use some sort of combination of those formulas, but that's before and that's after. It's really good to be able to sort of get this in your head as you read the question. Right? Takes a bit of practice, but we're going to sort of refer to this a few times, I think, during this question. Okay, part A. Determine the initial speed of the van. Show your working. Now, they said that the van experienced an impulse of 6,000 newtons. I should probably have highlighted this. There it is. Right. 6,000 newtons. Now, the van's going to slow down when it hits the car. It's going a certain speed, and when it hits the car, it's not going to speed up, it's going to slow down. So the way that its momentum was changed was in that direction. Right? It's almost like a strange way to apply the brakes. Right? So because the change in impulse of this thing is in that direction, we have to call it negative 6,000. And that's why here I've done negative 6,000. I'm using this. Right? The impulse equals the change of momentum. We're trying to find the initial speed of the van. We know everything there except u. Right? Impulse is minus 6,000. The mass of the truck, the mass of the van, pardon me, it was 2,000. I'm not adding the mass of the car. This is a question about the van. So this has to be all about the van. It's the van's impulse, the van's mass, the van's initial velocity or final velocity. Right? And the only thing that's missing is the initial velocity. It should be faster than 27 because we know this will slow it down. And sure enough, it is. U equals 30 meters per second, but that's how to figure it out. Pardon me. Okay, part B. Calculate the initial speed of the car. Well, same deal, right? Now, if the impulse on the truck was 6,000 that way, then the impulse of the car is 6,000 that way. It's a little bit like equal and opposite forces, right? Equal and opposite impulses as well. So exactly the same formula, but we're doing the same thing for the car now. So these are all the car's figures. Plus 6,000, weighs 1,200, ended up going 27. What was it doing at the start? 22. All right. Part C. The collision has a duration of 0.8 seconds. Okay, now you know you're going to have to use this, right? It's a collision. Impulse has been mentioned. They've given you a time now. I bet they're going to ask you for the force. Calculate the magnitude of the average force. Yep, exerted on the car by the van. Show you're working. Okay, we're just going to do this. Now, the only way you can get this wrong, this part C wrong, is getting the symbol wrong. All right. Calculate the magnitude of the average force exerted on the car by the van. This is the car's experience. The car is being forced. The car was forced forwards, so it's a positive 600, a 6,000, pardon me. Right? If we were getting the average force on the van was forced backwards. It didn't go backwards, it just slowed down in its forward motion, but it was being forced that way, in the negative direction. The car was being forced this way, so it's positive. Right? Solve that, 7,500 newtons. All right, let me just turn the page. Okay, Most vans don't have crumple zones at the front of the vehicles. We had a conversation about this not long ago in class. With reference to the average force exerted between objects during a collision, explain why crumple zones are effective. Why is a crumple zone effective? Okay. When you have a collision, let's say that you're going to come to a stop. Let's say you're going to, pardon me, let's say you're going to crash into a tree. You are going to go from 30 meters per second to 0. That's going to happen. It can happen fast or it can happen slow, but that's the impulse that's going to happen. If it happens fast, if it happens in a very small time, it's going to take a very big force, and it's the force that kills you. If the car has a crumple zone, and if the cockpit has an airbag, and if you're wearing a seatbelt, all that sort of stuff, that delays your slowing down time. That's you, the driver. You're slowing down time by a little bit. It makes the time much bigger, and that makes the force much smaller. The impulse is going to be the same. That truck driver felt 6,000 Newton seconds of impulse. That was unavoidable. He or she was going to experience 6,000. If we can spread that 6,000 over a longer time, that driver experiences a lesser force and won't die or won't break their bones or won't get damaged, right? It's the force that hurts you. And this is what I've said. So I've just stated the formula and said for the same impulse, because it will be the same impulse, a collision that takes more time experiences less force, meaning less damage and danger. All right. Okay, for the rest of question 4, I haven't even really put the answers up here because the answer sheet does a very good job here. First one says, in this experiment, if they're experimenting with different crumple zones, you can read that little stem yourself, identify one controlled variable that the car manufacturer needs to keep constant to ensure their investigation is valid, right? Remember, a valid investigation, the only thing that's allowed to change is what you're trying to change. And what they're trying to change here is the length of the crumple zone in the truck. So everything else has to stay the same, like the mass of the van, the mass of the car, the initial momentum of both of them, right? The collisions that they do have to all be in the same speed, and the impulse experienced due to the collision. Maybe the drivers as well, things like the condition of the car and the truck and the tires on the road, etc. But certainly they have to be traveling at the same speed. They have to basically do the same collision each time, right? So traveling at the same relative speed on the same surface, they literally have to do exactly the same movements and experience the same impulse every single time. All right, and part F, excuse me, says with reference to momentum, justify the variable identified in part E needs to why the variable identified in part E needs to be controlled. Well, it depends on which answer you say as to what you're going to say there, so I can't really answer that without taking half an hour by doing all of them. So I'm not. Question 5. Okay, this is an energy question. It's a work and energy question. Excuse me. Now, something you need to know, just in case you've forgotten it, is that work and energy are interchangeable. They're both measured in joules and they affect each other. If I do 5 joules of work on this pen, like by pushing it along here, right, I've now lost 5 joules of energy and it gained 5 joules of energy. Right? So work and energy are the same thing. Work is done on something when energy is transferred from one thing to another, or from one form to another. Work is done on something that changes kinetic energy into potential energy, for example. Right? So I'm assuming that you've paused the video and read this, right, before you've started listening to this. If not, pause the video and read it. But I'm just going to dive right into the answer here, okay? Again, there's a graph. Stop and look at it, okay? That force is in kilonewtons. That is something worth noting. It's thousands of newtons. That's not 160 newtons. That's 160,000 newtons. This is why you have a close look at the diagram. Right. They're trying to fool you. Don't be fooled. All right. Now, it says, calculate the work done by the train's engines during the 400 meters in acceleration. Okay, so it's the whole graph because that's the 400 meters. Sorry. Now, formulas for work and energy. Work equals the change in energy of something. I just said that. Work also equals the force on something times the displacement. Right? If you force something and it goes over a certain distance, the force times the distance equals how much work it took and how much energy it wasted, or how much energy that thing gained. All right. So calculate the work done by the train's engines during that. This is also the area under the graph, right? Because that's force and that's distance, right? And when you're multiplying these two things together, you literally get the area under the graph, the area of the whole graph, right? If it's one divided by the other, that's always the gradient, right? Rise over the run. This is rise times the run. So this is the area under the graph. So you've just got to figure out how much all that stuff comes to. Now, it doesn't matter how you do it. It's pretty easy. That's a triangle. That's a rectangle. That's another triangle. You can do it in threes. The book actually did it, not the book, the solutions section to this exam actually showed you that triangle, and then they did this as a trapezium. Right? Doesn't matter how you do it, just work it out. Right? It's grade 8 geometry. If you've forgotten your grade 8 geometry, it might be worth boning up on that a little bit, because things like this will come up. This is the second one we've had already. This is only our first exam. So this is how you do it. Again, just to quickly explain what you're doing. Right? Work equals F times D equals the area under the graph. And once you've done that, you can just go straight to there, by the way. You don't have to show any more working than that. You can just say, I've figured it out. Because the wisdom of the people who are going to mark your exam tells them that you couldn't possibly have guessed that. Right? Just show them that you know how it's done, and then show them that you've done it. That's okay. All right, part B. Determine the final speed of the train. Show you're working. Okay. Well, this is where we're going to get into this one here. Work equals change in energy. Right? If that much work was done, then that much energy was gained by the train. We have one extra little bit of information that we have to take into account here, and that's this. There's a constant resistive force of 2 by 10 to the 4 newtons acting against its motion. So it's not going to get all of that work changed into kinetic energy, because some of that work is fighting against this. So this is how you work this one out. Right? The total amount of kinetic energy is the work that was supplied to it minus the energy that was lost. Right? That work, this much, 2.4 by 10 to the 7 joules, some of it went to overcome that, and the rest of it went to give the train energy. Right? Those two numbers are going to add up to that. In other words, one of them is the work minus the lost energy. This is how you do it. And the lost energy, again, is force times D. Right? I know I've got them around the wrong way there. That's D times F. Okay. So the friction was doing work in the opposite direction, trying to slow the train down. And that's how much work it was doing. Right? So that's how much work the engines were doing. That's how much work was going against it. Right? And so the engines won by this much. So the train gained that much kinetic energy. Right? Now, to find out how fast it's going, you have to employ the kinetic energy formula, which has got V in it. Right? This is why we went this route. Okay, kinetic energy equals a half mv squared. Solve that for V, get the answer.